Right now, humanity controls exactly one planet. Every rocket we have ever launched, every astronaut who ever floated in microgravity, every probe that ever photographed a distant world, all of it represents a sphere of human presence, extending less than 1% of a single light year from Earth. We have barely left home, and yet we dream. We dream of colonizing Mars, reaching Alpha Centauri, spreading across the Milky Way. Scientists have designed engines that could theoretically carry us between stars. Engineers have sketched generation ships capable of voyaging for centuries. The physics works. The technology is imaginable. And yet, there is a barrier that no propulsion system can overcome. No artificial intelligence can solve. No automation can bypass. It is not a wall of energy or distance. It is something far more fragile. If you are ready to discover the true boundary of human expansion, hit that like button and subscribe. Now, settle in and make yourself comfortable. Let's begin. The fastest object humans have ever built is traveling away from the Sun at approximately 40,000 miles per hour. Voyager 1 launched in 1977, and after nearly 50 years of continuous flight, it has barely entered interstellar space. If this spacecraft were aimed at Proxima Centauri, our nearest stellar neighbour at just 4.2 light-years away, it would require approximately 73,000 years to arrive. The entire span of recorded human history would pass more than 10 times over. This is the first truth about interstellar travel that most people underestimate. The distances involved are not merely large, they are civilizationally incomprehensible. Consider the scale another way. Light, the fastest thing permitted by physics, requires 4 years and 3 months to travel from Proxima Centauri to Earth. A beam of light leaving that star when a child is born would not arrive until that child enters kindergarten. Yet light is almost infinitely faster than any spacecraft humanity can currently build. The gap between what physics allows and what engineering achieves spans factors of 10,000 or more. To appreciate what this means, imagine shrinking our solar system until the Sun becomes the size of a grain of sand. Jupiter would circle at 5 inches. Neptune, the outermost major planet, would orbit at approximately 30 inches from our sand-grained Sun. The entire solar system, every planet, every moon, every asteroid would fit comfortably on a dinner table. Now, find Proxima Centauri on this scaled model. Walk out of the room. Leave the building. Cross the street. Keep walking for approximately 4 miles. There, finally, sits another grain of sand representing our nearest stellar neighbour. 4 miles of empty space between 2 dust particles. And this represents the closest star to our Sun, a distance so short by galactic standards that astronomers consider it practically next door. Try yet another comparison to grasp what we are confronting. If you drove a car at highway speed 70 miles per hour, day and night without stopping, you would reach the Moon in approximately 5 months. You would reach Mars at its closest approach in roughly 70 years. You would reach Proxima Centauri in approximately 40 million years. Your descendants, driving that same highway for 40 million years, passing the wheel from generation to generation for a span of time longer than the entire existence of the human genus, would still be in transit. Or consider the comparison in terms of human voyaging across Earth itself. The first humans to reach Australia from Southeast Asia, perhaps 60,000 years ago, crossed approximately 90 kilometers of open ocean, a journey that probably took several days in primitive watercraft and represented the most ambitious voyage in human history to that point. If we scaled that journey up to interstellar distances, the equivalent crossing to Proxima Centauri would require not days, but approximately 3 billion years. The entire history of multicellular life on Earth would pass before arrival. The void between stars is not merely empty, it is emptiness on a scale that renders human experience meaningless. Try another comparison. If the distance from Earth to the Sun 93 million miles were compressed to the thickness of a single sheet of paper. The distance to Proxima Centauri would be a stack of paper over 70 feet tall. A single step for light becomes a 7-story building when translated to the scale of human experience. And Proxima Centauri is the nearest star. Most stars in our galaxy lie thousands or millions of times farther away. Or consider time rather than space. Light from Proxima Centauri that reaches your eye tonight began its journey during the last presidential administration. Light from stars visible to the naked eye departed years, decades, or centuries ago. The light from the Andromeda Galaxy began travelling 2.5 million years ago, when our ancestors were still learning to chip stone tools. When you look at the night sky, you see not the present but an archive of the past. Each star's light a message delayed by distances too vast for intuition to grasp. These numbers are not designed to inspire awe, though they may. They are designed to communicate a fundamental truth. The cosmos operates at scales that human intuition cannot grasp, and human institutions have never been tested against. Scientists and engineers have proposed numerous propulsion concepts that could theoretically close the gap between chemical rockets and the speeds required for interstellar travel. Each proposal reveals both the ingenuity of human engineering and the sobering reality of what even advanced technology can achieve. Nuclear pulse propulsion, first studied during the 1950s Project Orion, could potentially accelerate spacecraft to perhaps 3 to 5% of light speed by detonating nuclear bombs behind the vehicle. The concept sounds insane until you examine the mathematics. Each detonation pushes against a massive shock-absorbing plate at the spacecraft's rear. Thousands of explosions, carefully timed, could accelerate a vessel massing thousands of tons to velocities utterly beyond chemical rockets. The original Orion designers calculated that a spacecraft the size of a small city could carry hundreds of passengers to nearby stars within a century. The physics worked. The engineering, while challenging, seemed achievable with 1960s technology. General Atomics produced detailed designs. Freeman Dyson, one of the 20th century's most brilliant physicists, worked on the project and remained convinced throughout his life that it represented humanity's best near-term option for interstellar travel. At 5% of light speed, Proxima Centauri comes within reach in approximately 85 years, still longer than a human lifespan, but conceivably within the patience of a civilization. Alpha Centauri, a binary system containing 2 sun-like stars at 4.37 light-years distance, requires similar time. The project was cancelled. Not because it was impossible, but because the Nuclear Test Ban Treaty prohibited detonating atomic weapons in space. Political coordination failed before technical challenges could even be addressed. The pattern would repeat itself throughout the history of interstellar propulsion. The Orion cancellation deserves extended attention because it illustrates a pattern that would repeat throughout the history of interstellar ambition. The project did not fail because physics forbade it. The physics was sound. Nuclear explosions can indeed accelerate massive objects to interstellar velocities. The project did not fail because engineering was impossible. The engineering was challenging but within reach of 1960s technology. Indeed, some components were actually built and tested. The project failed because human institutions could not coordinate around it. The Nuclear Test Ban Treaty represented a legitimate attempt to reduce the risk of nuclear war. The diplomats who negotiated it were not thinking about interstellar travel, they were thinking about preventing atmospheric contamination and reducing international tensions. Their priorities were reasonable. Their concerns were valid. The treaty they produced may have prevented nuclear conflicts that would have killed millions, but the treaty also killed humanity's most plausible near-term path to the stars. Not through malice, not through short-sightedness, simply through the ordinary operation of human political coordination, which must balance competing priorities and cannot optimize for goals that lie centuries in the future. This pattern, technically feasible projects failing due to coordination problems rather than physical constraints, appears throughout the history of ambitious human endeavors. The superconducting supercollider, which would have been the world's most powerful particle accelerator, was cancelled in 1993 after billions of dollars had been spent, not because the physics was wrong, but because political support evaporated. The Space Shuttle program was designed to make space access routine and economical, but institutional pressures transformed it into an expensive and dangerous system that satisfied no one's original goals. The International Space Station took decades longer to build than planned, cost many times its original budget, and achieved only a fraction of its intended scientific program. Not because the engineering was impossible, but because international coordination proved more difficult than anticipated. If humanity cannot coordinate effectively around projects spanning decades, what hope exists for projects spanning centuries? More ambitious proposals push further toward the cosmic speed limit. Fusion-powered rockets, still beyond current engineering capability, might achieve 10% of light speed. These engines would burn hydrogen isotopes, deuterium and helium-3, at temperatures exceeding 100 million degrees, hotter than the core of the Sun. The reaction products, moving at significant fractions of light speed, would provide thrust far exceeding any chemical or fission rocket. The fuel exists in abundance. Deuterium can be extracted from seawater. Every gallon of ocean contains enough deuterium to equal the energy content of 300 gallons of gasoline. Helium-3, while rare on Earth, exists in vast quantities embedded in the lunar surface by billions of years of solar wind bombardment. A fusion economy, harvesting lunar helium-3, could theoretically fuel spacecraft capable of reaching nearby stars within human lifetimes. But fusion propulsion requires solving the same plasma confinement problems that have stymied fusion power generation for 70 years. Since the 1950s, fusion power has been 20 years away. A joke among physicists that captures the persistent gap between theoretical promise and engineering reality. Tokamaks and stellarators have demonstrated fusion reactions, but have never achieved sustained energy production. The engineering to create compact, reliable fusion engines for spacecraft remains decades or centuries away, if it proves possible at all. Antimatter propulsion represents the theoretical maximum of reaction-based propulsion. When matter meets antimatter, both annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation. No other reaction in physics achieves such efficiency. Chemical rockets convert less than 1/millionth of their fuel mass into energy. Fission reactions convert less than 1%. Fusion achieves slightly better. Only antimatter achieves total conversion. A fraction of a gram of antimatter, reacting with an equal quantity of normal matter, releases energy equivalent to the Hiroshima bomb, approximately 15 kilotons of explosive force from a quantity of fuel invisible to the naked eye. A few kilograms of antimatter could theoretically accelerate a spacecraft to 20% of light speed or more. The problem is production. Currently, humanity manufactures antimatter in quantities measured in nanograms per year, at costs exceeding trillions of dollars per gram. The total amount of antimatter ever produced by human civilization would not power a light bulb for a single second. Scaling production to the kilograms required for interstellar propulsion would require energy investments exceeding global civilization's total output for decades, perhaps centuries. The physics permits antimatter rockets. The economics forbids them for any foreseeable future. And even if economics could be overcome, the storage problem remains unsolved. Antimatter annihilates on contact with any normal matter, requiring containment in perfect magnetic vacuum indefinitely. Laser-pushed light sails offer a different approach entirely. Instead of carrying fuel, spacecraft would ride beams of light projected from massive arrays in the home system. Gossamer-thin sails, perhaps only molecules thick, would catch photons and accelerate continuously. Without the mass penalty of fuel, these craft could achieve significant fractions of light speed. The Breakthrough Starshot initiative proposes exactly this concept. At such velocities, Proxima Centauri lies approximately 21 years away. The probes would be tiny chip-sized spacecraft carrying cameras and communication equipment. They could not carry humans. They could not slow down upon arrival. They would streak through the target system in hours, capturing images and data before vanishing into the interstellar void forever. At 20% of light speed, journey times begin to feel almost manageable. 20 years is long, but governments have completed projects spanning such periods. The International Space Station required 15 years from initial agreement to first habitation. Major telescope projects spanned decades from conception to first light. The James Webb Space Telescope took over 25 years from initial proposal to deployment. But even these modest missions face challenges that illuminate the fundamental problem. The laser arrays required would need to maintain precise alignment for years during the acceleration phase. The organizational infrastructure to operate them would need to persist for the decades required for signals to return. The scientific institutions waiting to receive data would need to maintain interest in a mission launched before many of their researchers were born. 20 years seems short. But consider what has changed in the past 20 years on Earth. Nations have risen and fallen. Technologies have transformed daily life beyond recognition. Scientific paradigms have shifted. The world of 2005 differs radically from today in ways that would have been difficult to predict. The world of 2045 will differ equally radically from our present in ways we cannot now imagine. Will anyone still care about data from a mission launched a generation ago? This question haunts every interstellar proposal. The physics works. The engineering is challenging but imaginable. What remains uncertain is whether human civilization can maintain interest, funding, and institutional continuity across the timescales involved. And these timescales represent the optimistic scenarios, the nearest stars, the fastest theoretical propulsion, the smallest possible missions expand the scope, and the problem transforms from engineering challenge to civilizational impossibility. Proxima Centauri is not merely the nearest star, it is exceptionally, almost miraculously close by cosmic standards. The typical distance between neighboring stars in our galactic neighborhood measures roughly 5 light-years. Travel outward, and the gaps grow. Stars become sparser. Voids between stellar systems stretch across distances that would require millennia to cross, even at substantial fractions of light speed. Within 10 light-years of Earth, approximately 11 star systems exist. At 20% of light speed, reaching the farthest of these requires 50 years. Within 20 light-years, the number of accessible stars increases to roughly 95. Within 50 light-years, approximately 2,000 stars become theoretically reachable, but now voyages require 250 years minimum. Here, the mathematics begins revealing something troubling. 250 years ago, the American Revolution had not yet occurred. The Industrial Revolution was just beginning. Most humans lived in agricultural societies using technologies that would be unrecognizable to modern engineers. The fastest mode of transportation was the sailing ship. Information traveled no faster than a horse could gallop. Medicine consisted largely of superstition and bloodletting. The political entities that existed then, the British Empire, the Qing dynasty, the French monarchy, the Holy Roman Empire, the Ottoman Sultanate, have either transformed beyond recognition or ceased to exist entirely. The British Empire, that once controlled a quarter of Earth's surface, has contracted to a small island nation. The Qing dynasty collapsed over a century ago. The French monarchy was overthrown, restored, overthrown again, and replaced by 5 different republics. The Holy Roman Empire dissolved in 1806. The Ottoman Sultanate ended in 1922. Consider more recent history. The Soviet Union, which seemed permanent and powerful in 1980, ceased to exist 11 years later. Yugoslavia fragmented into 7 separate nations through a decade of bloody warfare. The European colonial empires that dominated Africa and Asia in 1940 had entirely withdrawn by 1970. The political map transforms continuously, and no configuration persists. Any civilization launching an interstellar mission faces this reality. This is not a technical problem. It is not a funding problem. It is not a political problem in any conventional sense. It is a problem built into the nature of human social organization itself, and this brings us to the real limitation that will echo through every chapter of this exploration. Civilizational coordination, decay, the inevitable degradation of institutional coherence, shared purpose, and collective memory across extended timescales represents the fundamental constraint on human expansion into the cosmos. Consider what we are asking. A mission lasting 250 years requires some organization to maintain the mission continuously across that span. Engineers must be trained to understand systems designed by people long dead. Social structures must transmit both technical knowledge and motivational commitment to people who never chose to participate. Every historical example suggests this is impossible. The Catholic Church, one of the longest continuously operating institutions in human history, has survived for approximately 2,000 years. But during that time, it has undergone massive transformations in doctrine, structure, and practice. The medieval church that launched the Crusades bears limited resemblance to the modern institution. Schisms have split it repeatedly. The Great Schism of 1054 separated Eastern and Western Christianity permanently. The Protestant Reformation of the 16th century fractured Western Christianity into thousands of competing denominations. The church that burned heretics at the stake is not the church that apologizes for historical persecutions. The church that sold indulgences is not the church that abolished the practice. The continuity is real but nominal, maintained through active reinterpretation rather than static preservation. Governments typically persist for far shorter periods. Political scientists have calculated that the average lifespan of a political regime measures decades, not centuries. The Roman Republic lasted approximately 5 centuries before transforming into the Roman Empire. And even that transformation represented a fundamental break in institutional continuity that contemporaries recognized as the death of the old order. The Roman Empire itself persisted in the West for roughly 5 centuries before fragmenting into successor kingdoms. The Byzantine continuation persisted longer, but underwent continuous transformation. The empire that fell to Ottoman conquest in 1453 shared little with the empire that Augustus founded except a claim to succession. Consider the history of China. Often cited as an example of civilizational continuity, the Chinese state has existed in some form for over 2,000 years, but this continuity masks radical discontinuity. The Han dynasty differed fundamentally from the Tang. The Song differed from the Ming. The Qing dynasty was founded by Manchu invaders who imposed foreign customs on the conquered population. The People's Republic represents yet another radical break. Mao explicitly sought to destroy traditional Chinese culture during the Cultural Revolution. The continuous Chinese civilization is a narrative constructed retrospectively, not a lived reality of institutional persistence. Each dynasty represented a new beginning, often achieved through bloody conquest and deliberate rejection of predecessor institutions. Corporations rarely survive a century. Of the companies listed in the original Dow Jones Industrial Average in 1896, none remain in the index today. The last original component, General Electric, was removed in 2018. The average lifespan of an S&P 500 company has declined from 67 years in 1920 to approximately 15 years today. The commercial enterprises that funded Voyager's launch have largely ceased to exist. Scientific institutions fare somewhat better but still demonstrate the pattern. The Royal Society, founded in 1660, has persisted for over 350 years, but its purposes, methods, and relationship to science have transformed utterly. The Royal Society of Newton's era functioned as a gentleman's club where natural philosophers presented demonstrations. The modern Royal Society functions as a professional organization, publishing peer-reviewed research, No human institution has ever maintained a complex mission with unchanged objectives for more than a few centuries. Even projects with clear endpoints, construction of specific structures, demonstrate coordination decay across extended timescales. The construction of medieval cathedrals spanned multiple centuries. Cologne Cathedral, begun in 1248, was not completed until 1880, a construction period of 632 years. But examine the history more carefully. Construction at Cologne stopped for approximately 400 years due to shifting priorities and resource constraints. The partially completed cathedral stood as a ruin through the Renaissance, the Reformation, and the Enlightenment. When work resumed in the 19th century, it was driven by German Romantic nationalism, a completely different motivation than the medieval religious devotion that began the project. The Sagrada Familia in Barcelona, begun in 1882, remains incomplete after nearly 150 years. The original architect, Antoni Gaudí, has been dead for a century. His successors work from incomplete plans, interpreting his intentions through fragmentary documentation. The building that will eventually be completed, perhaps by 2026, will reflect the interpretations of architects who never met Gaudí rather than his original vision. Interstellar missions cannot tolerate 400-year interruptions or rely on posthumous interpretation of fragmentary plans. Consider the Voyager missions themselves. Launched in 1977, they continue transmitting data to this day, nearly 50 years of continuous operation, but their maintenance is minimal. They require no human crew, no continuous decision-making, no institutional memory beyond basic tracking. Even so, the teams monitoring them have turned over completely multiple times. The engineers who built the probes have retired and died. Knowledge about the spacecraft's detailed operation has been lost and reconstructed as institutional memory faded. When Voyager 2 experienced an antenna-pointing anomaly in 2020, engineers had to reconstruct knowledge about software written before many of them were born. A crewed interstellar vessel would face incomparably greater challenges. Life support systems requiring continuous maintenance, propulsion systems requiring periodic adjustment, social structures requiring continuous governance, technical knowledge requiring continuous education, motivation requiring continuous reinforcement, and all of this must persist not across 40 years but across 200 or 500 or 1,000. The historical record provides even starker examples of institutional decay than those already mentioned. Consider the fate of classical knowledge after the fall of Rome. The Romans inherited Greek learning in mathematics, astronomy, philosophy, medicine, and engineering. They translated Greek texts into Latin. They built libraries. They established schools. They created the infrastructure for knowledge preservation that should have transmitted classical learning indefinitely. Within 3 centuries of Rome's fall, most of this knowledge had been lost in Western Europe. Not destroyed by invaders, much of it simply ceased to be copied as the institutions that maintained copying collapsed. The works of Aristotle vanished from European consciousness for 700 years, preserved only in Arabic translations that would eventually be translated back into Latin during the medieval period. Mathematical techniques that Romans used routinely. Techniques that would not be rediscovered in Europe for a millennium were forgotten as the schools that taught them closed, and the students who might have learned them turned to subsistence farming instead. The knowledge existed. The text survived in some locations, but the institutional infrastructure required to transmit knowledge across generations had collapsed, and with it collapsed the practical accessibility of learning that had taken centuries to accumulate. Or consider the fate of Chinese naval exploration. In the early 15th century, Admiral Zheng He commanded fleets of hundreds of ships, vessels far larger than anything Europeans would build for another century, on expeditions reaching as far as East Africa. China possessed the technology, the wealth, and the organizational capacity to establish a global maritime empire decades before European nations began their own age of exploration. Then, the expedition stopped. not because the ships sank or the technology failed, but because political priorities shifted. A new emperor favoured Confucian scholars who viewed maritime expeditions as wasteful extravagance. The great ships were left to rot. The records of the voyages were destroyed or suppressed. Within a generation, China had abandoned the seas and turned inward, leaving maritime exploration to Europeans who would use it to establish global dominance. The capability existed, the technology was proven. But institutional coordination failed, and with it failed a potential future that never materialized. These examples demonstrate something crucial about the relationship between capability and achievement. Having the physical capacity to accomplish something does not guarantee that the accomplishment will occur. Human institutions must also sustain the will, the coordination, and the continuity required to translate capability into achievement. And human institutions do not sustain these qualities indefinitely. The galaxy contains approximately 400 billion stars. Even the nearest 1,000 lie at distances requiring centuries of travel at any achievable speed. The Milky Way spans 100,000 light-years. At 20% of light speed, crossing the galaxy requires 500,000 years. 500,000 years ago, Homo sapiens did not yet exist. Our ancestor species, Homo heidelbergensis, roamed Africa and Europe using primitive stone tools. Modern humans emerged approximately 300,000 years ago. Anatomically, modern humans with modern behavioral complexity appeared perhaps 70,000 years ago. Civilization, cities, writing, agriculture began approximately 10,000 years ago. No human institution, no human language, no human culture has persisted for even 1% of the time required to cross the galaxy. Languages transform beyond recognition within a few thousand years. English speakers cannot understand Old English, spoken barely a millennium ago, without specialized training. The linguistic distance between modern English and the language of Beowulf is comparable to that between English and German. They are effectively different languages, sharing common ancestry rather than continuous traditions. Some might object that future humanity will be different. Perhaps we will develop new forms of social organization that persist longer than historical examples. Perhaps artificial intelligence will help us coordinate across timescales that defeated our ancestors. Perhaps the very importance of interstellar expansion will motivate commitment that less significant projects failed to inspire. These objections deserve serious consideration, but they also contain a hidden assumption that the future will be different from the past in precisely the ways required to make interstellar expansion possible. This is not analysis, it is hope, and while hope is valuable, it cannot substitute for realistic assessment of constraints. Every generation believes itself different from those that came before. The Romans believed their empire would last forever. They called it the Eternal City. The Victorians believed their empire would endure because it was founded on principles of liberty and progress that previous empires had lacked. The Soviets believed their system would outlast capitalism because it was based on scientific principles of historical development. All of these beliefs proved false. Not because the believers were foolish, but because they underestimated the forces of change that operate on all human institutions, regardless of their founding principles. There is no reason to believe that future institutions will be exempt from the coordination decay that has affected every institution in human history. The burden of proof lies with those who claim otherwise, and that proof has never been provided. This is why the physics of propulsion ultimately does not matter. Build engines that achieve 50% of light speed, accelerate to 90%, even at speeds approaching the cosmic speed limit. Galactic distances require timescales that exceed the demonstrated coherence of any human civilization. Suppose, against all historical precedent, a vessel maintains coherent purpose for 500 years and successfully reaches a star system 20 light-years away. Colonists establish themselves on a habitable world. They begin building a society. What is their relationship to Earth? A message sent home requires 20 years to arrive. The response takes another 20 years to return, 40 years for a single exchange. The grandchildren of the message's author receive replies meant for their grandparents. Economic coordination becomes impossible. Technical support becomes impossible. Political governance becomes impossible. The colony must become independent, not by choice, but by physics. And once independent, it will evolve. Languages will change, cultures will diverge, values will transform. Within centuries, colonists and their home civilization may no longer recognize each other as sharing common identity. The separation is built into the physics of distance and the biology of human lifespans. This brings us back to the real limitation: civilizational coordination decay. We can imagine the ships, we can design the engines, we can calculate the trajectories. What we cannot do is hold ourselves together long enough to use them. The barrier is not out there in the void between stars. The barrier is here, in the limited persistence of human purpose across generations. In the inevitable decay of coordination that afflicts every complex human endeavor as timescales stretch beyond institutional memory. No matter how advanced the technology becomes, this fundamental constraint remains. Not physics, not engineering. Us. The elegance of the generation ship concept lies in its apparent solution to human mortality. If individuals cannot survive voyages lasting centuries, perhaps communities can. Build vessels large enough to sustain thousands of people. Create enclosed ecosystems capable of recycling matter indefinitely. Design societies that persist across generations, with children born en route, eventually raising grandchildren who will finally arrive at distant destinations. The physics works. Engineers have sketched rotating habitats providing artificial gravity through centrifugal force. A cylinder 1 kilometer in diameter, rotating at approximately 1 revolution per minute, would generate Earth normal gravity at its outer rim. People living on the inner surface would experience weight. Could walk normally, could pour water that falls downward. The disorienting effects of rotation would be minimal at such scales. Ecologists have designed closed-loop life support systems. Plants convert carbon dioxide to oxygen while producing food. Bacteria break down waste into nutrients. Water cycles through purification and reuse. The theoretical efficiency of such systems approaches the natural biosphere that sustains Earth. A system that has operated continuously for billions of years. Architects have planned cities in space. The Stanford Torus, designed during a 1975 NASA summer study, envisioned a wheel-shaped habitat housing 10,000 people in a ribbon of land 1.8 kilometers in circumference. Sunlight, reflected through mirrors, would illuminate agricultural zones. The population could be self-sustaining indefinitely. More ambitious designs scale upward. The Island 3 concept proposed paired cylinders 32 kilometers long, each housing millions of inhabitants. At such scales, weather systems could form. Clouds could drift beneath artificial skies. Inhabitants might forget they lived in a spacecraft at all. What these designs universally fail to address is the transformation of the people themselves. Consider what happens when any human community becomes isolated. The process has occurred repeatedly throughout history, providing data that illuminates what generation ships would face. The Polynesian expansion across the Pacific began approximately 3,000 years ago from populations in Southeast Asia. Sailors in double-hulled canoes spread across the largest ocean on Earth, colonizing islands separated by thousands of miles of open water. Each settlement, once established, had limited contact with others. Voyaging was dangerous. Many islands were discovered once and never visited again by outsiders for centuries. The result was dramatic divergence, languages separated into distinct families. Hawaiian, Maori, and Tahitian all descend from common Polynesian roots, but speakers of one cannot understand the others without study. The divergence occurred across roughly 1,000 years of separation, far less than the timescales interstellar missions would require. Cultures developed unique characteristics. Hawaiian society evolved a rigid caste system with divine kings. Maori developed complex artistic traditions centered on wood carving and tattooing. Easter Islanders constructed the famous moai statues found nowhere else in Polynesia. Each population adapted to local conditions, elaborated local traditions, and forgot practices that were once universal. Technologies diverged as well. Some Polynesian populations lost the ability to make pottery, a skill their ancestors possessed. Others lost knowledge of bow and arrow construction. The Tasmanians, isolated from mainland Australia for approximately 10,000 years, lost technologies including bone tools, fishing with hooks, and possibly the ability to make fire. Small populations cannot sustain all the specialists required to maintain complex technological systems. Knowledge, not regularly used, gets forgotten. This process accelerates dramatically under conditions of total isolation. A generation ship departing Earth would, by necessity, become the most isolated human community in history. No new people would ever join. No emigrants would ever leave. No trade goods would arrive from outside. No ideas would filter in from neighbouring communities. All cultural input, all technological innovation, all genetic diversity would be limited to what departed with the original crew. The ship would be an island more isolated than any island on Earth, surrounded not by ocean but by vacuum, separated from the nearest human community, not by miles but by light years. Linguists have extensively documented how languages evolve in isolated populations. The process follows predictable patterns, governed by universal tendencies in human cognition and communication. Sound shifts alter pronunciation gradually but cumulatively. The Great Vowel Shift transformed English pronunciation between roughly 1400 and 1700, making Middle English text sound foreign to modern ears. Similar shifts occur in every language given sufficient time. Aboard a generation ship, pronunciation would drift continuously, with each generation speaking slightly differently than the last. Vocabulary adapts to local conditions. Words for irrelevant concepts fade from active use, and eventually from memory entirely. How long would shipboard inhabitants use words for beach or mountain or river? How many generations before such terms became archaic, then incomprehensible? Meanwhile, new terms would emerge for novel experiences, vocabulary for ship systems, for the social structures that developed aboard, for the psychological states unique to interstellar travel. Grammar simplifies in some areas while elaborating in others. Isolated languages often lose grammatical features that were present in ancestral tongues while developing new complexities in unexpected domains. Old English had grammatical gender for all nouns and complex case endings. Modern English has lost both. A shipboard language evolving over 500 years might transform equally dramatically. Within 5 generations, perhaps 150 years, the shipboard language would become significantly different from the departure tongue. Speakers might still communicate with Earth through effort, as English speakers can understand Scots English or Jamaican patois with concentration. Within 10 generations, mutual intelligibility could be compromised. Conversation would require translation. Technical documents from Earth would need interpretation. By the time descendants of the original crew reach their destination after 500 years, they might struggle to read their ancestors' technical manuals without specialized training. The language in which the ship's systems were designed, the language in which maintenance procedures were written, would have become a dead language studied by scholars, but not spoken by the population that depended on those systems for survival. This is not speculation. Linguistic drift at these rates is well documented on Earth, where isolation is far less complete and cultural exchange remains possible through trade, warfare, and migration. The complete isolation of a generation ship would intensify every factor that drives language change. But language represents merely the most easily quantified dimension of cultural transformation. More fundamental changes would reshape shipboard society in ways that no one could predict or control. Consider the mission's purpose. The original crew understood why they left. They chose to abandon Earth, knowing they would never see their destination. Their motivation, whether scientific curiosity, colonial ambition, religious calling, or flight from catastrophe, was personal and immediate. They experienced the decision. They felt the sacrifice. They carried memories of Earth that made the journey meaningful. Their children, born aboard the ship, inherit none of this. The second generation never chose to be on a vessel traveling through interstellar void. They never saw Earth. They never experienced the society they left behind. The destination exists for them only as a promise, something their parents described, a place in stories rather than a goal connected to their own desires. For these children, the ship is not a vehicle carrying them somewhere. The ship is home, the corridors they walk, the compartments they inhabit, the faces they see daily. These constitute their entire world. Earth is a legend. The destination is a myth. Only the ship is real. The original mission was their parents' quest, not their own. By the third generation, even second-hand memory of departure fades. Grandchildren hear stories about Earth from grandparents whose own memories are childhood impressions of a world they left at age 10 or 20. These stories become family legends, growing less detailed and less emotionally resonant with each retelling. The fourth generation knows Earth only through formal education history lessons about a place as remote as ancient Rome is to modern Americans. By the fifth generation, the departure has become mythology. The founders are ancestor figures, perhaps revered, perhaps resented, but not understood as real people who made comprehensible choices. Their motivations seem as alien as the motivations of pyramid builders or crusaders seem to contemporary minds. Human societies transmit purpose across generations through institutions, religious traditions, national narratives, educational systems, but these institutions require reinforcement from the broader culture to maintain their power. Religious practice persists because communities gather to worship, because ritual marks life transitions, because social pressure maintains observance, because sacred sites anchor belief to physical reality. The Catholic Church maintains continuity partly through the physical presence of Rome, of ancient cathedrals, of relics and artifacts connecting present practice to ancient tradition. National identity persists because symbols surround citizens daily, because monuments commemorate shared history, because education systems transmit canonical narratives, because borders define who belongs and who does not. American identity draws on physical landscapes. Plymouth Rock, Independence Hall, the Statue of Liberty that anchor abstract values in concrete experience. Aboard a generation ship, all of these mechanisms would necessarily be artificial constructs, designed by the ship's architects and implemented by its social engineers. The nation is the ship itself. But how does one feel patriotic toward a spacecraft? The religion must be invented or transplanted. But transplanted religions, severed from their sacred landscapes and ancestral communities, typically transform beyond recognition within centuries. The history begins with departure and accumulates slowly as decades pass, but a history spanning only a few generations provides thin soil for identity to root. Whether such constructed institutions can maintain coherent purpose across 500 years represents an untested question. Nothing in human experience suggests they can. History offers many examples of purpose degradation in closed communities. The trajectory is remarkably consistent, regardless of the community's founding ideology. Utopian colonies, founded with intense ideological commitment, typically last 1 to 3 generations before their founding vision fragments or collapses. The Shakers, who established communities throughout the northeastern United States in the late 18th century, maintained their distinctive practices for roughly a century before membership collapsed. The Oneida community, founded on radical principles of shared property and complex marriage, lasted only 33 years before converting to a conventional joint stock company. Brook Farm, the transcendentalist experiment, survived barely 6 years. Religious communities, sustained by powerful spiritual motivation, rarely maintain doctrinal purity beyond a few centuries without schism or reform. Christianity split into Eastern and Western branches within a millennium of its founding. Protestantism fragmented into thousands of denominations within centuries of Luther's Reformation. Buddhism divided into Theravada, Mahayana, and Vajrayana traditions, each containing countless schools and lineages. Even communities explicitly designed to preserve unchanging tradition monastic orders, for example, experience continuous evolution in practice and interpretation. Political ideologies, initially held with revolutionary fervor, moderate or transform within decades of achieving power. The Soviet Union's founding ideology bore limited resemblance to the system that collapsed in 1991. Revolutionary France transformed through republic, empire, restoration, and multiple subsequent republics. The People's Republic of China abandoned core Maoist economic principles within decades of Mao's death. No community has ever maintained unchanged ideological commitment for the 500 years a typical interstellar mission would require. What replaces original purpose when it fades? The answer, observed repeatedly in closed communities, is faction formation and internal conflict. Humans naturally organize into competing groups. We are tribal primates, evolved to form coalitions that compete for resources and status. When external challenges are absent, when no predators threaten, no enemy armies mass at borders, no natural disasters demand collective response, internal competition fills the void. Aboard a generation ship, with no external enemies and limited resources, factional conflict would likely emerge within generations. The factions might form along any available axis of difference. Families with more descendants might compete against those with fewer. Inhabitants of different ship sections might develop rivalries. Those who operate critical systems might seek privileges denied to others. Religious or philosophical differences, initially minor, might amplify into fundamental divisions. Some factions might advocate changing the mission. Perhaps the destination chosen by the founders no longer seems optimal. Perhaps newly discovered information suggests a better target. Perhaps the current generation simply does not want what their ancestors wanted. These reformers would push to alter course, adjust ship systems, modify social structures. Other factions would defend original plans. Traditionalists would argue that the founders' wisdom should not be second-guessed, that changing course would betray ancestral sacrifice, that the mission's integrity requires adherence to original parameters. These conservatives would resist any modification, viewing change as betrayal. The conflicts between these groups could become violent. History provides abundant examples of communities tearing themselves apart over ideological differences. The wars of religion devastated Europe for over a century. The English Civil War set neighbour against neighbour. Ideological purges in revolutionary states killed millions. A generation ship, offering no possibility of separation or emigration, would trap opposing factions in permanent proximity. Even non-violent disagreements could fracture the community into hostile camps, occupying different ship sections. Communication between groups might cease. Cooperation on shared infrastructure might fail. The unified mission would dissolve into competing tribes, sharing a vessel but no longer sharing purpose. The history of closed religious communities, frontier settlements, and isolated research stations demonstrates this pattern repeatedly. People living in enforced proximity, with limited options for exit, develop intense interpersonal conflicts. Small irritations magnify into feuds. Minor disagreements escalate into schisms. The same faces, seen daily for years or decades, become unbearable. Antarctic research stations, despite housing small populations for only months at a time, experience psychological stress severe enough to require careful screening of personnel. Submarine crews, confined together for deployments lasting weeks, develop conflicts requiring active management by commanding officers. The generation ship environment, offering no exit whatsoever across multiple human lifetimes, would intensify these pressures beyond anything previously experienced. This brings us back to the real limitation, and here we must be explicit about why it matters. All of this still fails because no technological solution addresses civilizational coordination decay. Some theorists have proposed that artificial intelligence could solve the problems of purpose, degradation, and factional conflict. Design governing systems that maintain mission continuity regardless of crew preferences. Program objectives that cannot be overridden by human decisions. Create machine overseers that ensure continued progress toward the destination despite whatever social transformations occur aboard. This solution fails for reasons that illuminate the fundamental nature of the barrier we face. Artificial intelligence systems, however sophisticated, cannot generate human motivation. They cannot create meaning. They can process information and execute commands, but they cannot make people care about objectives. Consider what it would mean to live under machine governance that enforced mission parameters against the population's will. The AI maintains course toward a destination that current inhabitants did not choose and may not want. It allocates resources according to mission requirements rather than popular preferences. It prohibits modifications that might compromise original objectives. This is tyranny benevolent by design, perhaps, but tyranny nonetheless. Human beings resist tyranny. They circumvent rules. They sabotage systems. They find ways to assert autonomy against imposed control. A population that has lost interest in reaching its destination will not be persuaded by machine dictates. They will resist, circumvent, or simply ignore their mechanical overseers. The machines cannot force humans to want things. They cannot instill purpose. They cannot create the motivational commitment that interstellar missions require. They can only coerce, and coercion, sustained across centuries, eventually fails when the coerced population loses all investment in the system that constrains them. Moreover, artificial intelligence systems themselves require maintenance across centuries. Hardware degrades, circuits fail, storage media corrupt, mechanical components wear. No machine built by humans has ever operated continuously for 500 years. The longest operating human artifacts are static objects, stone monuments, preserved documents, not active systems requiring continuous function. Software encounters situations its designers did not anticipate. Programs that operate flawlessly for decades eventually face circumstances that trigger unexpected behaviors. The more complex the system, the more likely it contains latent bugs that manifest only under rare conditions, conditions that become increasingly likely across centuries of operation. Systems developed by engineers who have been dead for generations must be maintained by people trained through educational chains that have themselves mutated unpredictably. The linguistic drift discussed earlier affects technical vocabulary as surely as everyday speech. The conceptual frameworks used to understand ship systems would evolve across generations. Maintenance procedures clear to the original designers might become opaque to their distant descendants. If the human institutional capacity to maintain mission continuity has failed, the technical capacity to maintain complex artificial intelligence systems will have failed alongside it. The machines depend on the same organizational persistence they are meant to preserve. The AI solution imagines that technology can substitute for human coordination. But technology itself requires human coordination to function. The machines cannot maintain themselves. They cannot train their own technicians. They cannot preserve the knowledge required to repair and update their own systems. When the human institutions fail, the machines fail with them. The generation ship concept also assumes that arriving generations will want to complete their ancestors' mission. But why should they? Consider the psychological reality of approaching a destination after 500 years of travel. The arriving generation has spent their entire lives aboard a vessel. Every person they have ever known lived aboard the ship. Every experience they have ever had occurred within its hull. The ship's environment, its corridors, its compartments, its rhythms of day and night, its social structures, is the only reality they have known. The destination world is alien. Its gravity may differ from the artificial gravity they have experienced since birth. Its atmosphere may smell strange, contain unfamiliar compounds, require adaptation. Its terrain bears no resemblance to the manufactured landscapes of the ship. Everything the arriving generation knows exists aboard the ship. Everyone they love, every place they consider home, every comfort they have ever experienced lies within the vessel that has carried their community across the void. Why would they leave? The psychological challenge of disembarking from a generation ship onto a new world may prove as difficult as the journey itself. Colonization requires establishing new infrastructure from scratch on an undeveloped planet. It requires adapting to new environments that the colonists have never experienced. It requires facing new risks, unknown pathogens, unstable geology, extreme weather that shipboard life eliminated entirely. For a population whose culture has evolved across 20 generations of shipboard existence, the destination represents not home, but exile. Landing means abandoning everything familiar for everything strange. It means leaving the only world they know for a world they have seen only in images and simulations. Historical analogues suggest that some colonization efforts may simply stop at this final barrier. Arriving populations may find their vessel more comfortable than the unknown world below. They may choose to remain in orbit, harvesting resources from the planetary system, but never descending to surfaces their ancestors chose. But they did not. They may establish orbital habitats, expanding their shipboard existence rather than abandoning it. This outcome would not represent mission failure in any technical sense. The ship arrived, the destination was reached, the voyage succeeded, but the purpose establishing human presence on planetary surfaces, expanding Earth's biosphere to new worlds, would remain unfulfilled because the people capable of fulfilling it no longer wish to do so. The founders, who sacrificed everything to begin the journey, would not recognize their descendants' choice as fulfilling their vision. But the founders have been dead for centuries. Their preferences have no power over people who never knew them. There is another psychological dimension that generation ship proposals rarely address: the existential horror of the voyage itself. Consider what it means to live your entire life in transit. You will never arrive, your parents will never arrive, your children will never arrive, generations will live and die in the void between stars, and you are one of those generations. Your existence serves only as a link in a chain. You inherit the mission from ancestors and pass it to descendants, but you yourself will never experience its fulfillment. Every meaningful human culture provides frameworks for understanding death. Religious promises of afterlife, secular concepts of legacy, artistic notions of work that outlasts its creator. But generation ship passengers face a unique existential challenge. Their entire lives are instrumental, meaningful only as means to ends they will never witness. How do humans psychologically survive such conditions? The honest answer is that we do not know. No human community has ever faced comparable circumstances. The closest analogues: prisoners serving life sentences. Patients with terminal diagnoses typically maintain hope of reprieve or find meaning in present experience, rather than distant future outcomes. Generation ship passengers would have neither option. Some would adapt. Humans are remarkably flexible in the meanings they construct, but others would not. Depression, nihilism, and despair would likely affect significant portions of the population. Suicide rates might rise. Birth rates might fall, as people question the ethics of bringing children into lives of perpetual transit. These psychological pressures would compound the social and cultural challenges already discussed. A population struggling with existential despair would be even less capable of maintaining the institutional coherence that interstellar missions require. All of this brings us back to the real limitation. Generation ships fail not because life support cannot be maintained or because propulsion systems break down. The community that departs is not the community that arrives. Language transforms until technical manuals become indecipherable. Culture evolves until ancestral motivations seem incomprehensible. Values shift until founding purposes lose their grip. Factions form and splinter the unified mission into competing interests. Arriving generations may not want what departing generations chose, and this transformation cannot be prevented by technology. Faster engines do not help. If journey time is reduced to 200 years, the problem diminishes but does not disappear. 200 years still exceeds the demonstrated persistence of any human ideology or institutional structure. The Shakers lasted less than 200 years. The Soviet Union lasted less than a century. Even the United States, often cited as a stable polity, has transformed fundamentally multiple times across its 250-year existence. Better life support does not help. Physical survival is not the challenge. The Stanford Torus designs, the Island 3 concepts these can theoretically sustain human bodies indefinitely. What they cannot sustain is human purpose. Psychological and cultural survival is the barrier, not biological survival. Artificial intelligence governance does not help. Machines cannot generate human meaning. They cannot force humans to retain purposes they have abandoned. They cannot maintain themselves without human institutional support. When human coordination fails, machine coordination fails alongside it. The barrier is not engineering. The barrier is the fundamental nature of human societies, their continuous evolution, their inevitable fragmentation, their limited capacity to preserve coherent objectives across generational time. Generation ships represent humanity's most ambitious attempt to overcome the mortality that limits our reach. If individuals cannot survive the journey, surely communities can. Surely we can design social systems that persist where biological systems fail. But social systems are biological systems, emergent properties of biological minds interacting across time. They are subject to the same evolutionary pressures that shape all living things. They adapt, transform, and eventually become something their ancestors would not recognize. The generation ship is not a solution to interstellar distances. It is a demonstration that the problem is not distance at all. The problem is us. We cannot build institutions that persist unchanged for 500 years. We cannot transmit purpose without transformation across 20 generations. We cannot create societies that maintain coherent objectives across timescales that exceed our demonstrated capacity for coordination. The generation ship carries humans across interstellar distances, but it does not carry human civilization intact. The civilization that departs transforms during the voyage into something new, something that owes limited allegiance to ancestral objectives and may have no interest in fulfilling missions chosen by people who died centuries before. This is civilizational coordination decay in its purest form. Not technology failing, but coordination failing. Not machines breaking, but human purpose fragmenting. Not physics imposing limits, but human nature imposing limits. And those limits cannot be engineered away. The physics permits the journey. The engineering can theoretically support the voyage. What fails is the social fabric that would need to hold across centuries for the journey to fulfill its purpose. We can design ships capable of traveling between stars. We cannot design human societies capable of maintaining coherent purpose across the journey times involved. The vessel that arrives at a distant star may carry biological humans, but it will not carry the civilization that departed. That civilization will have transformed, fragmented, or collapsed during the voyage. Something new will have replaced it, something that evolved in isolation, shaped by pressures no one anticipated. What happens when these transformed communities actually reach their destinations? What becomes of the colonies they might establish? the answer reveals that the barrier extends far beyond the voyage itself, and the implications grow more severe with every light year of expansion. Assume for the moment that every previous objection can be overcome. Assume generation ships somehow maintain mission continuity across centuries. Assume arriving populations retain enough connection to their founders' purposes to actually disembark onto new worlds. Assume infrastructure is established, populations grow, and functioning human civilizations emerge around distant stars. What then? The answer reveals why interstellar expansion eventually halts regardless of initial success, and why the barrier lies not in reaching other stars but in what happens afterward. The moment a colony becomes self-sufficient, the clock begins counting down toward independence. Not political independence declared through revolution or negotiation, a far more fundamental separation imposed by physics itself. Consider the communication reality facing a colony established 20 light-years from Earth. A message sent home requires 20 years to arrive. The response requires another 20 years to return. 40 years pass between a question and its answer. 40 years. In 40 years, a newborn becomes middle-aged, with children of their own. Governments rise, transform, and fall. Technologies that seemed cutting-edge become obsolete museum pieces. The person who sent the question may have died before the answer arrives. The experts who formulated the response may be addressing problems that were solved decades ago, or problems that ceased to exist when the systems that created them were abandoned. What kind of coordination is possible under these conditions? Economic coordination fails immediately. Trade, the engine of complex civilization, requires responding to supply and demand across manageable timescales. Markets function because information about scarcity and surplus travels faster than goods themselves. A merchant who learns that wheat is scarce in a distant city can profit by shipping wheat there before prices normalize. This arbitrage mechanism allocates resources efficiently across geographic distances, but the mechanism depends entirely on information speed. A merchant on Earth who notices resource scarcity in a colony 20 light-years away cannot profit from this knowledge. By the time a resource shipment arrives decades after departure, assuming any ship could be dispatched at all, conditions will have changed beyond prediction. Consider a specific scenario. Earth detects that Colony Alpha, established around a star 20 light-years away, desperately needs medical equipment. A plague has struck. Hospitals lack the specialized devices required for treatment. Earth's manufacturers can produce the equipment within months. Earth dispatches the shipment. If ships travel at 5% of light speed, an optimistic assumption, the medical equipment arrives 400 years after departure. 400 years. The plague has long since run its course. The patients who needed treatment have been dead for centuries. Their grandchildren's grandchildren have lived and died. The hospitals that needed equipment have either developed local alternatives, been abandoned, or been replaced by entirely different medical systems shaped by 4 centuries of independent development. The medical equipment, when it arrives, addresses a problem that exists only in historical archives if anyone still reads those archives. If anyone can still understand the language in which they were written. This is not a contrived example. It is the inevitable reality of interstellar economics at any plausible speed. Even at 20% of light speed faster than any propulsion system yet designed could achieve, the shipment arrives 100 years after departure. 100 years transforms every economic calculation into speculation about a future no one can predict. Consider how much Earth itself has changed in the past century. In 1925, antibiotics had not been discovered. Commercial aviation barely existed. Computers were theoretical concepts. Television was experimental. The entire infrastructure of modern life, smartphones, internet, satellites, nuclear power, lay decades in the future. No one in 1925 could have predicted what goods would be valuable in 2025. No merchant in 1925 could have profitably shipped goods to arrive a century later. The goods that were scarce then are abundant now. The goods that are scarce now did not exist then. Interstellar trade requires making exactly such predictions, but across even longer timescales and with even less information about conditions at the destination. Consider even more granular examples of how communication delays destroy economic coordination. Insurance cannot function across interstellar distances. Insurance requires assessing risks, pricing premiums, and paying claims within timeframes that allow the insured party to benefit. A colony that suffers catastrophic crop failure cannot wait 40 years for an insurance claim to be processed. The colonists will have starved, adapted, or died of other causes long before compensation arrives. Banking cannot function. Loans require that borrowers and lenders agree on terms, that payments be tracked, that defaults be addressed. A colony that borrows from Earth institutions to fund infrastructure development cannot make payments on a 40-year communication cycle. By the time Earth confirms receipt of a payment, the colony's economic situation will have transformed beyond recognition. Compound interest calculated across such spans would produce absurd results, debts that exceed the total economic output of entire worlds, or credits so large they become meaningless. Contracts cannot function. Any agreement between Earth and colony parties requires enforcement mechanisms that operate within relevant timeframes. A contract dispute that takes 40 years to adjudicate is not a contract, it is a historical curiosity. The parties who signed the original agreement will be dead before any court can rule on its interpretation. Corporations cannot function across such distances. Modern corporations coordinate the activities of thousands or millions of people toward common objectives. This coordination requires communication that operates faster than the timescale of business decisions. A corporation with divisions on Earth and a colony 20 light-years away would effectively be two separate organizations, unable to share information, unable to coordinate strategy, unable to respond to each other's circumstances. Even family relationships cannot meaningfully persist. A child born on Earth who sends a message to grandparents on a distant colony will be middle-aged before any response arrives. The grandparents may have died decades before their words reach their grandchild. Family connections that normally span generations through visits, conversations, and shared experiences would be reduced to exchanges of historical documents, messages from the dead to recipients who have become strangers. Every institution that binds human civilization together, economic, legal, social, familial, requires communication that operates faster than the timescales of human life and human decision-making. Remove that communication, and the institutions dissolve. The fundamental premise of trade that sellers can respond to buyer needs within relevant timeframes dissolves across interstellar distances. Interstellar trade is impossible, not because ships cannot carry cargo, but because information cannot travel fast enough to make trading decisions meaningful. Technical support fails with equal certainty. Consider the complexity underlying modern technology, a complexity we rarely appreciate because the systems work invisibly. A smartphone contains components manufactured on 6 continents, using materials mined from dozens of countries, processed through supply chains involving thousands of specialized facilities. The chip inside required photolithography machines that only 3 companies on Earth can manufacture: ASML in the Netherlands, Nikon, and Canon in Japan. Those machines themselves required components from hundreds of suppliers, each representing decades of specialized development. A single semiconductor fabrication plant costs $10 to $20 billion and requires thousands of engineers with highly specialized training. The chemicals used in chip production, photoresists, etchants, dopants, require their own manufacturing infrastructure. The precision instruments that measure chip performance require their own supply chains. The software that designs the chips requires teams of specialized programmers working for decades. No colony could replicate this infrastructure. The population would be too small, the specialist pools would be too shallow, the supply chains would be too truncated. But the problem extends far beyond semiconductors. Pharmaceutical production requires specialized chemical synthesis, purification equipment, analytical instruments, and quality control systems. Developing a new drug requires thousands of scientists working for years, supported by manufacturing capabilities that themselves require decades to develop. A colony facing a novel disease could not simply manufacture the required medications. They would need the entire pharmaceutical supply chain, from chemical feedstocks to manufacturing equipment, to trained pharmacologists to regulatory systems ensuring safety. Aerospace manufacturing requires metallurgical expertise, spanning dozens of specialty alloys, precision machining accurate to millionths of an inch, testing infrastructure capable of simulating flight conditions, and quality control systems, ensuring that every component meets exacting specifications. A colony whose spacecraft failed could not simply build replacements. They would need the entire aerospace industrial base that took Earth's civilization a century to develop. Medical imaging equipment, MRI machines, CT scanners, PET scanners requires superconducting magnets cooled to near absolute zero, specialized radiation detectors, and calibration systems that only a handful of facilities on Earth can produce. A colony whose imaging equipment failed would lose diagnostic capabilities that modern medicine depends upon. Even seemingly simple technologies embed hidden complexity. A ballpoint pen requires precision manufacturing of the ball bearing at its tip, specialized ink formulations, and materials science to create the housing. A colony could perhaps manufacture crude writing implements, but the gap between crude writing implements and modern ballpoint pen represents decades of industrial development. The technical support problem extends beyond individual expertise to encompass the entire structure of technological civilization. Modern technology does not consist of isolated devices that can be understood and maintained independently. It consists of vast interconnected systems where every component depends on countless others. Consider something as simple as a light bulb. To manufacture a light bulb requires glass, which requires sand mining, smelting, and forming. It requires tungsten filaments, which require mining tungsten ore, refining it to pure metal, and drawing it into fine wire. It requires inert gas fill, which requires separating gases from the atmosphere through fractional distillation. It requires brass bases, which require mining copper and zinc, alloying them in precise proportions, and machining them to exact specifications. It requires insulating materials, adhesives, quality control instruments, packaging materials, transportation systems, and electrical infrastructure to power. A simple light bulb embeds the output of dozens of industries, hundreds of specialized processes, and thousands of person-years of accumulated knowledge. Thomas Edison did not just invent the light bulb, he had to invent the entire electrical system, from generators to wiring to sockets, because the bulb was useless without the infrastructure to power it. Now, multiply this complexity by the thousands of technologies that modern civilization depends upon. Every technology rests on a pyramid of supporting technologies, each of which rests on its own pyramid of supporting technologies, recursively down to raw materials and basic scientific knowledge. A colony cannot replicate this pyramid. The population is too small, the industrial base is too narrow, the supply chains are too truncated. The colony can bring finished products, it can bring documentation, it can bring some specialists, but it cannot bring the living industrial ecosystem that produces and maintains technological civilization. That ecosystem exists only on Earth, and it cannot be transported. When a colonial engineer faces a problem requiring any of these capabilities, they cannot consult experts on Earth. The consultation would require 40 years minimum. By then, the engineer has either solved the problem through local innovation, developed workarounds using available materials, or died while the problem remained unsolved, perhaps taking irreplaceable knowledge to the grave. Technical knowledge must be self-contained at each colony. Every colony must independently possess the expertise required to solve every problem it might encounter, but no colony can possess complete technical knowledge. Earth's technological civilization rests on billions of specialists, each mastering narrow domains while depending on others for everything outside their expertise. A cardiologist depends on electricians to power the hospital, farmers to provide food, software engineers to maintain medical records, mining companies to extract materials for equipment, chemical plants to produce medications, and millions of other specialists whose skills the cardiologist does not possess. The system functions because communication and transportation enable specialization and exchange. Any specialist can access any other specialist's expertise within hours or days. The global network of specialization creates capabilities that no individual or small group could possess. Colonies cannot replicate this system. Their populations are too small. A colony of 100,000 people, large by colonization standards, requiring enormous ships and resources to establish, could sustain perhaps 10,000 specialists across all fields. 10,000 people to cover medicine, engineering, agriculture, manufacturing, education, administration, and every other domain required for technological civilization. Earth requires billions to maintain current capabilities. 10,000 specialists could not maintain even a fraction of that capability. Problems that Earth solves routinely through expert consultation become existential crises for colonies that lack the relevant expertise and cannot access it remotely. Political governance faces identical barriers. Earth-based authorities, assuming Earth maintains any coherent authority across the timescales involved, cannot respond to colonial events meaningfully. Imagine a colonial government facing constitutional crisis. Two factions claim legitimate authority. Violence threatens. The colonial governor requests guidance from Earth. Which faction should be recognized? Which constitutional interpretation is correct? Earth receives the request 20 years after transmission. Scholars debate. Lawyers analyze. Politicians deliberate, assuming the political system that originally authorized the colony still exists, which after 20 years is far from certain. A carefully reasoned response is crafted and dispatched. 20 more years pass. The response arrives 40 years after the crisis began. By then, one faction has won. The other has been destroyed, exiled, or integrated into the new order. A new constitution has been written, implemented, modified, and possibly replaced. The governor who requested guidance has been dead for decades, perhaps executed by the winning faction, perhaps honored as a founding figure, perhaps forgotten entirely. Earth's carefully reasoned response addresses a political situation that exists only in historical records. Even more absurdly, the response might arrive in a language the colonists no longer fully understand. 40 years of linguistic drift, in conditions of total isolation, would produce significant divergence. The legal terminology that seemed precise to Earth's lawyers might be unclear to colonial descendants whose vocabulary has evolved in different directions. This is not a problem that faster communication can solve. Even at light speed, the absolute maximum possible for information transfer, the round trip takes 40 years. Light-speed communication does not help when the communication delay exceeds human planning horizons. Colonial populations will necessarily develop local governance, capable of acting on local timescales. They must. The alternative is paralysis, waiting decades for permission to address immediate problems, while those problems compound and multiply, and the people affected by them live and die without resolution. The colonies must govern themselves. This is not ideology. This is physics. And self-governing colonies, experiencing different environments, facing different challenges, developing different solutions, inevitably diverge from their parent civilization. This process has occurred repeatedly throughout human history, even when communication delays measured days or weeks rather than decades. European colonies in the Americas maintained regular communication with their homelands. Ships crossed the Atlantic in weeks. Mail travelled continuously. Administrators shuttled between colony and metropole. Trade goods flowed in both directions. Yet divergence proceeded relentlessly within generations. American English diverged from British English within 2 centuries. Words that meant one thing in London meant something different in Boston. Spellings diverged. Americans dropped the U from colour and honour, changed centre to centre, developed vocabulary unknown in Britain. Idioms emerged that puzzled speakers on the other side of the Atlantic. American religious practice evolved differently than European tradition. The Great Awakening swept through colonial America with emotional intensity that seemed excessive, even fanatical, to European observers. Denominations that barely existed in Europe, Baptists, Methodists, and eventually uniquely American movements like Mormonism, flourished in American soil. American political institutions developed unique characteristics that would have seemed strange or impossible in European contexts. The written constitution as supreme law, the federal system dividing power between states and national government, the separation of powers among branches, the Bill of Rights protecting individual liberties against government power, all represented adaptations to American circumstances that Europeans found difficult to understand. Within 3 centuries, a brief span by historical standards, the relationship between colony and metropole had transformed from dependency to rivalry to estrangement. The American Revolution did not create American distinctiveness. It ratified a separation that had already occurred culturally, economically, and psychologically, and these colonies maintained regular communication with their homelands. Interstellar colonies would not. The historical record suggests a clear progression. Fragmentation, followed by divergence, followed by loss of common identity. Consider the fate of Roman Britain after the legions withdrew in the early 5th century. For 400 years, Britain had been part of the Roman world, connected by roads, trade routes, and administrative systems to Mediterranean civilization. Latin was the language of government and education. Roman law governed transactions. Roman engineering provided infrastructure: roads, aqueducts, heated baths, stone buildings. Roman currency facilitated trade. Roman military protection provided security. When the legions withdrew, Britain was not conquered or destroyed. It was simply isolated. Within 2 generations, urban civilization collapsed. The cities that had sustained Roman-style life were abandoned as populations dispersed to rural areas where subsistence was easier. The roads fell into disrepair without the administrative systems that had maintained them. The aqueducts ceased functioning without engineers who understood their operation. The heated baths went cold without fuel supplies and maintenance expertise. Within 2 centuries, the descendants of Roman Britons were living in small villages, farming with primitive tools, governed by warrior chieftains rather than Roman law. The sophisticated economy that had connected Britain to continental trade networks had been replaced by local subsistence. The knowledge of Roman engineering, how to build arches, how to make concrete, how to construct heated floors had been lost. Literacy nearly vanished. The Latin language survived only among clergy, preserving religious texts, and even that preservation was imperfect, as demonstrated by the grammatical errors that accumulated in copied manuscripts. This was not foreign invasion, though Anglo-Saxons did eventually arrive and accelerate the transformation. This was civilizational simplification, resulting from isolation. A population cut off from the networks that sustained complex civilization regressed to whatever complexity it could maintain independently. The Roman Britain example deserves deeper examination because it illustrates how quickly and completely technological regression can occur. Roman Britain possessed technologies that would not be matched again for over 1,000 years. Roman concrete, a mixture of volcanic ash, lime, and seawater, produced structures that have survived 2 millennia and inspired modern engineers seeking more durable building materials. This technology was completely lost. Medieval Europeans could not produce anything comparable. Roman central heating, The hypercore system that circulated hot air beneath floors and through walls provided comfortable temperatures in cold climates. This technology was completely lost. Medieval Europeans huddled around open fires while Roman ruins with intact heating systems stood nearby. Roman plumbing lead pipes, aqueducts, public fountains, sewage systems provided clean water and sanitation at scales that would not be matched until the 19th century. This technology was completely lost. Medieval London, built near the ruins of Roman Londinium, suffered repeated plague outbreaks that Roman sanitation practices might have prevented. The Romans knew how to build roads that remained usable for centuries with minimal maintenance. They knew how to survey land accurately across long distances. They knew how to administer complex organizations, census populations, collect taxes, and maintain legal systems across vast territories. All of this knowledge was lost, not destroyed, but allowed to lapse as the institutions that maintained it collapsed. Roman books contained the knowledge. Roman ruins demonstrated the results. But without the educational infrastructure to transmit knowledge and the organizational infrastructure to apply it, the knowledge might as well not have existed. It was present, but inaccessible, visible, but unusable. The same fate awaits isolated colonies, but worse. Roman Britain was part of a larger world. Trade continued with the continent. Missionaries brought literacy. Eventually, medieval Europeans rediscovered classical learning through contact with Arab scholars who had preserved it. Isolation was incomplete, and recovery eventually became possible. Interstellar colonies would have no such lifelines. No trade ships would arrive with forgotten technologies. No missionaries would bring literacy to populations that had lost it. No contact with preserved knowledge elsewhere would enable rediscovery. What is lost would be lost permanently. The regression was not immediate. It took generations. People tried to maintain Roman ways, but each generation that grew up without access to Roman supply chains, Roman education, Roman expertise, possessed less capability than the generation before. The knowledge that required continuous practice to maintain was not practiced. The skills that required institutional support to transmit were not transmitted. The complexity that required population-scale coordination to sustain was not sustained. Interstellar colonies would face identical pressures and more extreme isolation. This brings us back to the real limitation, and we must state it with absolute clarity. All of this still fails because civilizational coordination decay operates at every scale of the expansion process, and no technology can overcome it. The assumption underlying every vision of interstellar expansion is that colonies will maintain high technology. They will continue building spacecraft. They will preserve the industrial capacity to manufacture advanced equipment. They will retain the scientific knowledge accumulated on Earth across millennia of development. Historical evidence suggests otherwise. When complex civilizations become isolated, they typically lose capabilities rather than maintaining them. It follows from the relationship between population size and technological complexity. Complex technologies require specialists. Specialists require training. Training requires institutions. Institutions require populations large enough to sustain them. The Tasmanians lost bone tools, fishing technology, and possibly fire-making across 10,000 years of isolation. A population of a few thousand could not sustain the specialists required to maintain even Paleolithic-level technologies indefinitely. But the Tasmanian example, often cited, actually understates the problem facing interstellar colonies. Tasmanian technologies were simple by modern standards. Stone tools, wooden implements, techniques passed through direct demonstration from parent to child. Even these simple technologies proved unsustainable in a small, isolated population. Interstellar colonies would possess far more complex technologies and would require far larger specialist populations to maintain them. Consider what it takes to maintain a single modern technology. Semiconductor fabrication, chip manufacturing requires chemical engineers who understand photoresist chemistry. the light-sensitive materials that allow circuit patterns to be transferred to silicon. It requires physicists who understand plasma, etching the process that carves circuit patterns into chip surfaces. It requires materials scientists who understand silicon crystal growth, the techniques that produce the pure, defect-free wafers on which chips are built. It requires optical engineers who understand photolithography, the projection systems that focus circuit patterns onto chip surfaces with nanometer precision. It requires mechanical engineers who understand cleanroom systems, the environmental controls that prevent contamination. It requires electrical engineers who understand chip architecture, the logic designs that determine what chips can do. It requires software engineers who understand design automation, the programs that convert circuit specifications into manufacturing instructions. Each of these specialties requires years of training. Each training program requires instructors who themselves received years of training. Each instructor requires a career path that justifies the investment positions in industry, academia, or research that employ the skill continuously. On Earth, millions of people work in the semiconductor industry. Thousands of educational programs train new specialists each year. The system is self-sustaining because the population is large enough to support continuous training and employment across all required specialties. A colony of 100,000 people cannot sustain this system. Perhaps they bring a few semiconductor specialist engineers who understand some aspects of chip production, but those specialists age and eventually die. Their knowledge must be transmitted to successors. If the colony lacks the educational infrastructure to train successors, if no young person shows aptitude, if other priorities demand attention, if the colony's semiconductor equipment fails before training completes, if the written documentation proves insufficient without hands-on mentorship, the knowledge dies with its last holder. And once lost, knowledge is extraordinarily difficult to recover. Earth developed semiconductor technology through decades of trial and error, building on foundations of physics and chemistry that themselves required centuries to develop. The knowledge embedded in a modern chip fabrication plant represents the accumulated learning of millions of person-years of research and development. A colony that loses this knowledge cannot simply reinvent it. They would need to repeat the entire developmental process, but without the large populations, the research institutions, the industrial infrastructure, and the accumulated prior knowledge that made the original development possible. The process of technological loss would not be gradual and uniform. It would be sudden and catastrophic, following cascade patterns that amplify small failures into civilizational collapse. Consider how modern technological capabilities depend on each other. If semiconductor fabrication capability is lost, computers can no longer be manufactured. Without new computers, the systems that control power grids, communication networks, water treatment plants, and transportation systems cannot be maintained. As these systems fail, the capabilities they support, manufacturing, healthcare, agriculture, governance, degrade in turn. Each failure triggers further failures in systems that depended on the original capability. This cascade pattern has been observed in smaller-scale technological collapses. When the Soviet Union dissolved, the integrated economic systems that had connected member states fragmented. Factories that depended on inputs from other republics could not function. Supply chains that had been managed centrally collapsed. Technologies that required coordination across the former Soviet space became unmaintainable. The result was not gradual decline, but sudden collapse. Living standards in some former Soviet states fell by 50% or more within years. Interstellar colonies would face similar cascade risks, but without any possibility of external support to arrest the collapse. A colony that loses one critical capability does not simply lack that one capability. It loses everything that depended on that capability, which in turn causes losses in everything that depended on those secondary capabilities, propagating outward until a new equilibrium is reached at a much lower level of complexity. The new equilibrium might be very low indeed. A colony that loses electronic technology loses not just computers but also modern medicine, modern agriculture, modern manufacturing, and modern communication. The surviving population would need to reconstruct civilization from a technology base comparable to the 18th or 19th century. But without the accumulated libraries, the abundant fossil fuels, the untapped mineral deposits, and the stable climate that enabled Earth's original industrialization, the colonies would not immediately regress to Stone Age conditions. Initial equipment, brought from Earth, would function for generations if maintained carefully, but maintenance itself requires capabilities that erode. When the last semiconductor fabrication equipment fails, no more semiconductors are produced. When the last technician who understands fusion reactor maintenance dies without training a successor, the reactors operate until they fail, then stop forever. Colonies would stabilize at whatever technological level their populations could sustain, likely comparable to 18th or 19th century Earth, with significant local variation depending on population size, resource availability, and which knowledge happened to survive the initial simplification. But this stable level would not include interstellar capability. The implications are devastating for dreams of galactic expansion. The colonies cannot build new ships. The industrial base required for spacecraft manufacture, mining, refining, metallurgy, electronics, propulsion systems, life support far exceeds what any colony could sustain. They cannot mount rescue missions to failing sister colonies. Even if they wanted to help, even if they knew help was needed, they would lack the capability to provide it. They cannot send expeditions to further stars. The dream of compound expansion, each colony spawning new colonies in an ever-widening wave, requires colonies that can build ships. Colonies that cannot build ships are endpoints, not waypoints. They cannot even maintain communication with Earth once their original equipment degrades beyond local repair capability. The transmitters fail, the receivers fail. The knowledge to repair them has been lost. Silence descends. They become islands, trapped at their destinations, regressing toward technological levels sustainable by their populations, developing along trajectories shaped entirely by local conditions, forgetting over generations that other human worlds exist. Some colonies might retain higher capabilities than others. Larger populations could sustain more complex industries. Colonies established on resource-rich worlds might support more specialists. Favorable environments might allow larger populations that maintain more sophisticated capabilities longer, but none would retain full Earth-level industrial capacity indefinitely. All would simplify over time, as the irreplaceable components of their initial infrastructure failed and could not be rebuilt, and simplified colonies cannot contribute to interstellar expansion. Some optimists suggest that colonies could maintain coordination through extreme redundancy, sending thousands of specialists in each field, carrying multiple copies of all documentation, building backup systems for every critical capability. This approach misunderstands the nature of the problem. Redundancy helps with random failures. It does not help with systematic failures. If the problem is that populations are too small to sustain specialist training across generations, sending more specialists in the initial group merely delays the problem, it does not solve it. The colony begins with 100 metallurgists. They age, they train successors, but training the next generation of metallurgists requires not just existing metallurgists, but also educational infrastructure, schools, laboratories, apprenticeship systems, career paths that motivate students to pursue metallurgy rather than other professions. If this infrastructure does not exist or cannot be maintained, the metallurgists will not be replaced. Within a century, the original 100 metallurgists have died. Perhaps 50 successors were trained. Within another century, those 50 have died, and perhaps 20 successors were trained. The capability is declining generationally, and no amount of initial redundancy prevents this decline. It only extends the time frame. The same dynamic applies to every specialized capability the colony possesses. Each generation transmits less than it received. Each generation loses capabilities that previous generations maintained. The colony does not maintain equilibrium. It continuously declines until it reaches a level that its institutions can actually sustain. That sustainable level is far below Earth's current technological civilization. How far below depends on local circumstances, but below, nonetheless. Earth might continue launching missions for as long as Earth-based civilization persists, but Earth-based civilization also faces coordination decay. Over millennia and galactic expansion requires timescales measured in millennia. At minimum, the political will to fund interstellar expansion would fade. The original motivations, whatever they were, would lose urgency. The generations that remembered why expansion mattered would age and die. Their successors, facing immediate problems and lacking visceral connection to ancestral aspirations, would redirect resources toward present concerns. Economic priorities would shift. Cultural attitudes would transform. The original motivations would be forgotten, and the colonies, isolated and simplifying, could not take up the banner. No matter how advanced the technology becomes, this pattern reasserts itself. Civilizational coordination decay prevents further expansion regardless of physical capability. The Roman Empire extended across the Mediterranean world, maintaining roads, aqueducts, legal systems, and military coordination for centuries. Then it fragmented. Knowledge was lost. Capabilities disappeared. Regions that once sustained advanced urban civilization reverted to subsistence agriculture. This process would occur throughout an interstellar civilization, not because of invasion or disaster, but because isolation inherently produces regression. The galaxy may eventually contain human-descended populations on thousands of worlds. The expansion might achieve that much before coordination collapse halts it everywhere. But these populations would not constitute a civilization. They would share common origins, as the speakers of English, Hindi, Russian, and Greek share Indo-European origins without sharing contemporary identity. They would perhaps share some elements that resisted transformation, universal human tendencies toward language, tool use, social organization, but they would not coordinate. They would not communicate meaningfully. They would not recognize each other as members of a common project. They would be cosmic orphans, isolated on their separate worlds, maintaining whatever complexity their populations could sustain. Developing along trajectories shaped entirely by local conditions, forgetting over millennia that they ever shared a common origin or common purpose. The dream of galactic civilization assumes that what works locally can scale infinitely. But human coordination does not scale infinitely. It breaks down across distance and time. The further we expand, the more completely we fragment. This is why the real boundary of human expansion is not set by physics or engineering. It is set by the fundamental nature of human society, its inability to maintain coherence across scales that exceed institutional memory, that separate generations from their ancestors' purposes, that isolate populations beyond meaningful communication. The colonies diverge. They simplify. They forget, and the expansion ends. Not in triumph, but in fragmentation. Not with a galactic civilization, but with scattered islands of humanity, each developing alone, each following its own trajectory toward futures their common ancestors could never have imagined. The preceding analysis permits a tentative answer to the question that began this exploration. The answer is not measured in light years that our engines could theoretically cross. It is not determined by the energy our civilizations could theoretically muster. It is not limited by any physical constant or engineering constraint that future technology might overcome. The answer is measured by the timescale across which human civilizations can maintain coherent purpose. And that timescale has hard limits that no technology can extend. Based on historical evidence accumulated across every human civilization that has ever existed, this timescale measures roughly 500 to 1,000 years for complex technological projects requiring continuous institutional support. Longer duration endeavors occasionally persist, but typically experience fundamental transformation rather than continuous execution of original objectives. The project that exists after 1,000 years bears limited resemblance to what began. No human institution has ever maintained a complex mission with unchanged objectives for more than a few centuries. Not religious orders, not governments, not scientific programs, not commercial enterprises, not cultural movements. The pattern holds across every culture, every era, every level of technological development. It appears to be a fundamental characteristic of human social organization rather than a contingent feature of particular historical circumstances. This is not pessimism. This is observation. At 20% of light speed, an optimistic assumption requiring propulsion technologies not yet developed and perhaps never achievable, humanity could theoretically reach stars approximately 100 to 200 light-years. From Earth before civilizational coordination, decay makes further expansion impossible. Journey times to stars at this distance would range from 500 to 1,000 years, approaching the outer limit of demonstrated institutional persistence. At more realistic speeds, perhaps 5% of light speed, achievable with extensions of currently understood physics such as nuclear pulse propulsion, the limit shrinks dramatically. At 5% of light speed, a journey of 100 light-years requires 2,000 years. This exceeds any demonstrated capacity for human coordination by factors of 2 to 4. The practical limit at realistic speeds might be 50 light-years or less. Distances reachable within 500 to 1,000 years, the zone where institutional memory might barely persist if every favorable condition aligned. What would this neighborhood actually look like? Within 50 light-years of Earth, approximately 2,000 stars exist. The majority are red dwarfs, small dim stars that burn their hydrogen fuel so slowly they will shine for trillions of years. Whether red dwarfs can host habitable planets remains uncertain. Their habitable zones lie so close that any planet warm enough for liquid water would be tidally locked, with one face in permanent daylight and one in permanent darkness. Whether human colonies could thrive in such environments is unknown. Perhaps 50 to 100 stars within 50 light-years are G-type stars similar to our Sun, providing familiar radiation environments for Earth-descended life. Including the slightly cooler K-type orange dwarfs that might also host habitable worlds, perhaps 150 stars could theoretically support human colonies. Some fraction of these, perhaps 20 to 40, likely host rocky planets in their habitable zones. A successful expansion, one that somehow maintained coordination across the maximum demonstrated timescales, might establish human presence on perhaps 10 to 30 worlds. More optimistically, if propulsion technology exceeded current projections and institutional persistence reached historical maximums, presence might extend to 50 or even 100 worlds across 100 light-years. Let us be concrete about what this limited expansion would actually entail. The closest potentially habitable exoplanets we have detected include Proxima Centauri b, approximately 4 light-years away, orbiting a red dwarf star in conditions that may or may not permit liquid water. TRAPPIST-1, approximately 40 light-years away, hosts 7 Earth-sized planets, several of which may be habitable, but TRAPPIST-1 is also a red dwarf, and whether its planets can support life remains unknown. The closest Sun-like stars with confirmed planets include Tau Ceti, approximately 12 light-years away, and Epsilon Eridani, approximately 10 light-years away. Neither has confirmed habitable planets, but both are targets for continued observation. If we assume that perhaps 1 in 10 Sun-like stars hosts a potentially habitable planet, a rough estimate consistent with current observations, our 50 light-year neighborhood might contain 20 to 40 target worlds. Reaching these worlds at 5% of light speed would require between 80 and 1,000 years depending on distance. Reaching them at 20% of light speed, if such speeds ever become achievable, would require between 20 and 250 years. Establishing self-sustaining colonies would require massive initial investments. Ships capable of carrying thousands of colonists with all necessary equipment would dwarf any spacecraft humanity has ever built. The energy required to accelerate such ships to interstellar velocities would exceed humanity's current annual energy production. The coordination required to build, launch, and support such missions would need to persist across generations. If everything went perfectly, if the technology was developed, if the coordination was maintained, if the ships reached their destinations, if the colonies survived their early years, humanity might, over several centuries, establish presence on perhaps a dozen worlds within 50 light-years. A dozen worlds in a galaxy of 400 billion stars. This is the ceiling. This is the maximum achievable expansion, assuming every optimistic assumption proves correct, and the ceiling might never be reached. The coordination challenges discussed throughout this exploration suggest that most expansion attempts would fail before achieving even this modest goal. The realistic outcome might be presence on 2 or 3 nearby worlds, or no expansion at all, as generation after generation fails to maintain the institutional commitment required to launch interstellar missions. This would represent a genuine achievement. A dozen worlds bearing human-descended life would constitute an expansion beyond anything our ancestors could have imagined when they first looked up at the stars, but it would not represent galactic civilization. The Milky Way contains approximately 400 billion stars spread across 100,000 light-years. A dozen worlds within 50 light-years represents presence in approximately 1/1000th of galactic territory. If the galaxy were reduced to the size of the United States, human expansion at its theoretical maximum would cover an area smaller than a single house, and even this modest neighborhood would fragment over time. The fragmentation would begin immediately. Colonies separated by 20 light-years cannot coordinate meaningfully. Each colony would necessarily develop independent governance, independent economic systems, independent cultural institutions. Within 200 years, 5 generations, colonies would begin to feel like foreign countries, rather than extensions of Earth civilization. Language drift would make communication difficult. Cultural divergence would make mutual understanding harder. Technological divergence, as different colonies retain different capabilities, would create gaps that widened over time. Within 500 years, colonies and Earth might struggle to recognize each other as sharing common heritage. The languages would be as different as modern English, from Anglo-Saxon, technically related but mutually incomprehensible without specialized study. The cultures would have developed in directions shaped by local environments rather than shared history. Within 1,000 years, the colonies would be as different from each other and from Earth as China is different from Brazil, or Japan from Nigeria. Common ancestry would be historical fact, acknowledged in textbooks and origin myths, but irrelevant to contemporary identity. Within 10,000 years, still a brief span by evolutionary standards, colonial populations might be unable to reproduce with each other or with Earth humans. Different gravities, different atmospheres, different diets, different radiation environments, and potentially different applications of genetic technology would drive biological divergence. The descendants of humanity would have become multiple species, related only through chains of descent too long for meaningful connection. This is not coordinated expansion. This is speciation. This is the creation of separate lineages that share common origins but will follow separate destinies. Some have proposed that artificial intelligence might transcend these limitations. Design machine intelligences with stable goals. Program objectives that persist unchanged across any timescale. This proposal misunderstands the nature of the problem at multiple levels. First, artificial intelligence systems require maintenance, updates, and repairs. Hardware degrades over centuries. Cosmic radiation damages circuits in ways that accumulate over time. Mechanical components wear. Software encounters situations its designers did not anticipate, producing errors that compound as edge cases multiply. These systems depend on civilizations capable of building replacements, debugging errors, and providing support infrastructure. The machines are not self-sufficient. They are extensions of the civilizations that created them, dependent on those civilizations for their continued function. If human civilizations cannot maintain coherent technological capability across interstellar timescales, they cannot maintain the artificial intelligence systems meant to substitute for them. When the institutions fail, the machines they created fail alongside them. Second, artificial intelligence systems face their own version of coordination decay. Machine learning systems trained on human data inherit human biases and limitations. Systems designed to pursue specific goals encounter situations where those goals conflict, become undefined, or produce outcomes their designers would not endorse. The alignment problem, ensuring that artificial intelligence systems continue pursuing objectives their creators intended, remains unsolved, even for systems operating over years, let alone millennia. An AI system operating for centuries without human oversight might drift from its original objectives through accumulated errors, unexpected environmental inputs, or the simple fact that any goal specification comprehensive enough to guide behavior across unforeseeable circumstances has not been, and perhaps cannot be, created. The artificial intelligence proposal faces an additional challenge that is rarely discussed. Human values have transformed dramatically over historical time. Practices that seemed obviously correct to our ancestors, slavery, human sacrifice, absolute monarchy, religious persecution, strike modern people as obviously wrong. Practices that seem obviously correct to us will likely seem obviously wrong to our descendants. Values are not fixed. They evolve. An artificial intelligence system designed today would embed contemporary values. Over millennia, human values would continue evolving. The AI's values would not evolve with them. That is, after all, the point of using AI to maintain stable objectives across time. But this means that the AI's objectives would increasingly diverge from what human descendants actually value. The machine that set out to fulfill humanity's dreams would eventually be working toward objectives that humanity's descendants consider misguided, irrelevant, or actively harmful. What should such an AI do when it reaches its destination? It carries objectives programmed by long-dead creators. The descendants of those creators, if any exist, hold different values. Should the AI follow its original programming or defer to the values of living humans? There is no satisfying answer. An AI that follows original programming ignores the wishes of actual living beings in favor of the wishes of long-dead programmers. An AI that defers to living humans abandons the stable objectives that were supposed to be its advantage over human institutions. The artificial intelligence proposal does not escape the problem of value coordination across time. It merely transforms the problem into a different form. The problem of programming values that remain appropriate across timescales, during which human values themselves transform. Third, and most fundamentally, artificial intelligence expansion does not fulfill the dream that motivates interstellar ambition. The aspiration underlying human interest in the stars is not merely to send representatives throughout the cosmos. It is to expand human experience, human awareness, human presence. The dream is that humanity, the species, the civilization, the continuity of consciousness and culture will persist and spread. Robots spreading through an empty galaxy, while humanity remains confined to a few dozen worlds, would not constitute cosmic significance for our species. It would constitute cosmic irrelevance dressed in the appearance of achievement. We did not dream of the stars so that machines could visit them while we stayed home. The machine solution solves the wrong problem. It addresses the question of how to cross distances while ignoring the question of why crossing distances was supposed to matter. This brings us to a question that has haunted astronomers since they first understood the scale of the cosmos and the age of the galaxy. Where is everyone? The Fermi paradox, named for physicist Enrico Fermi, who allegedly posed the question during a lunch conversation in 1950, observes a troubling discrepancy between expectations and observations. The galaxy is approximately 13 billion years old. Stars and planets capable of supporting life have existed for perhaps 10 billion years. If intelligent life arises with any frequency, if even one civilization per million suitable stars develops technology, the galaxy should have been colonized many times over by now. The mathematics is straightforward. Even at expansion rates far below light speed, even with technologies no more advanced than we can currently imagine, a determined civilization could spread across the entire galaxy in a few million years. A civilization arising 1 billion years ago would have had time to cross the galaxy hundreds of times. Yet, we observe no evidence of such expansion. No alien megastructures, dimming distant stars. We have surveyed millions of stars and found nothing. No radio signals from technological civilizations. We have listened for decades and heard only silence. No ancient probes entering our solar system. Our skies are empty of artificial visitors. The galaxy appears empty of technological intelligence despite conditions that should have produced abundant intelligent life. Various explanations have been proposed. Perhaps intelligent life is rare. Perhaps the emergence of intelligence requires such improbable circumstances that Earth may be the only example in the galaxy or even the observable universe. The chain of events from simple chemistry to technological civilization includes many steps, each of which might be improbable. Single-celled life might be common, while complex multicellular life is rare. Complex life might be common, while intelligence is rare. Intelligence might be common, while technological civilization is rare. Perhaps technological civilizations typically destroy themselves through nuclear war, environmental collapse, artificial intelligence catastrophe, or other existential risks before they can spread beyond their home worlds. The same technologies that enable interstellar travel might also enable self-destruction, creating a filter that eliminates civilizations before they can expand. Perhaps they exist, but choose not to communicate deliberately, hiding from cosmic dangers we do not yet understand, or observing us without interference like wildlife researchers watching gorillas, or simply uninterested in contact with primitive species like ourselves. Perhaps they exist but communicate in ways we cannot detect, using technologies beyond our comprehension, or operating at scales or timescales we cannot perceive, or having transcended physical existence entirely. But civilizational coordination decay suggests another answer, an answer that requires no great filter, no universal self-destruction, no deliberate hiding. Not because intelligence is rare. Intelligence might arise frequently on planets throughout the cosmos. The galaxy might have produced billions of technological species across its history. Not because civilizations destroy themselves, some surely do, but the universality of destruction seems unlikely. Surely some civilizations among billions would survive their dangerous technologies. Rather, because intelligence that remains coordinated across interstellar distances may be impossible for any species, regardless of technology or biology. Every species that achieves technological civilization may face the same barrier we face, the limited coherence of social organization across timescales that exceed institutional memory. Consider what this implies. 1 billion years of galactic history. Millions of species achieving technological civilization across that span. Each species dreams of the stars. Each develops propulsion technologies. Each launches missions toward nearby worlds. Each establishes colonies, and each fragments. The colonies diverge from their homeworlds within centuries. The homeworlds lose interest in expansion as generations pass and priorities shift. The colonies simplify, as isolation takes its toll on technological complexity. Communication ceases as equipment fails and cannot be replaced. Within millennia, brief spans by galactic timescales, each expansion effort dissolves into scattered islands of intelligence, isolated on their separate worlds, no longer capable of the coordinated action that would make their presence visible across cosmic distances. The galaxy fills with life, but no unified civilization ever emerges. No empire spans the stars. No federation coordinates among distant worlds. No galactic community develops. Each world develops independently. Each follows its own trajectory. Each forgets its cosmic origins as the generations pass and the records decay. The silence we observe is not evidence of absence. It is evidence of fragmentation. This interpretation of cosmic silence deserves additional consideration because it transforms our understanding of humanity's place in the cosmos. If the silence results from civilizational fragmentation rather than civilizational absence, then intelligence may be far more common than the silence suggests and far more tragic. Imagine a galaxy in which billions of species have achieved technological civilization across billions of years. Each species dreams of cosmic significance. Each reaches for the stars. Each establishes colonies on nearby worlds, and each fragments. The process plays out again and again across billions of years. Species after species achieves the capability for interstellar travel. Species after species fails to maintain the coordination required for interstellar civilization. The galaxy fills with the scattered descendants of countless intelligent lineages, but no unified civilization ever emerges to connect them. Each inhabited world is an island of consciousness in a cosmic ocean. Each island knows, in some abstract sense, that other islands exist. The physics that enables their own existence must enable existence elsewhere. But no island can communicate with any other. No island can coordinate with any other. Each develops alone, following its own trajectory toward futures that no other island will ever know. This is not a galaxy empty of intelligence. It is a galaxy saturated with intelligence, but intelligence that is fundamentally, inescapably isolated. The cosmic silence is not evidence that we are alone. It is evidence that we are all alone. Together, countless species sharing a galaxy they can never share. If this interpretation is correct, it transforms the emotional meaning of our cosmic situation. We are not unique. We are not special. We are one of billions of species who achieved exactly what we achieved, dreamed exactly what we dreamed, and faced exactly the barrier we face. There is strange comfort in this. We are not failing where others succeeded. We are facing a universal constraint that every species faces. Our limits are not our shame, they are our nature, shared with every other intelligence that has ever contemplated the stars. The galaxy may be filled with the descendants of countless intelligent species, scattered across thousands or millions of worlds. But each world would be an island. Each population would have regressed to whatever complexity its local environment sustains. Each would have forgotten its origins, lost its founding technologies, developed its own languages and cultures and beliefs unrelated to those of ancestral populations. None would be capable of the coordinated action, the sustained, multi-generational, institutionally coherent effort that would make its presence visible across cosmic distances. We would not detect them because there is nothing to detect. No radio signals because the transmitters were not maintained. No megastructures because the coordination to build them exceeded species capacity. No colonization waves because the waves fragmented before spanning significant distances. The cosmos might be alive with intelligence, more alive than any previous answer to the Fermi paradox suggests, and simultaneously silent, because every intelligence faces the same constraints we face. We are not alone, we are simply isolated, as every intelligence is isolated by the same fundamental constraints. This isolation is not tragic. It is clarifying. It means that what matters is here, now, on this world and perhaps on the few neighbouring worlds we might successfully reach. The cosmic expansion we imagined was always a dream beautiful, motivating, inspiring generations of scientists and engineers and dreamers, but ultimately incompatible with what we are. The dream served a purpose. It gave us reasons to develop technologies, to look outward, to imagine futures beyond our immediate circumstances. The engineers who designed nuclear pulse propulsion, the astronomers who catalogued exoplanets, the dreamers who wrote science fiction about galactic federations, all contributed to human flourishing, regardless of whether the dream itself was achievable. But the dream was never the point. And yet, recognizing the limits of human expansion need not produce despair. It offers instead an invitation to reconsider what matters. Human significance does not require galactic conquest. This statement contradicts assumptions so deeply embedded in modern culture that many will resist it instinctively. We have been taught that growth is good, that expansion represents success, that species that spread survive while those that remain confined eventually perish. The narrative of cosmic expansion carries emotional weight precisely because it promises escape from the mortality that constrains individual human lives. If we cannot live forever, perhaps our civilization can. But this narrative contains hidden assumptions that do not survive examination. The meaningfulness of human experience does not scale with the volume of space we occupy. A civilization spanning 1,000 worlds is not 10 times more meaningful than one spanning 100 worlds. The experiences, relationships, achievements, and insights that constitute human flourishing occur at human scales in individual lives, in communities, in the accumulated wisdom passed between generations. A galactic empire would not experience more meaning than a planet-bound civilization. It would simply spread the same quantum of meaning across a larger volume. The value of human civilization does not increase with each additional star system added to our dominion. What makes civilization valuable? Knowledge, art, justice, love. The accumulated achievements of countless generations striving toward better futures does not require cosmic scale to matter. The Library of Alexandria, destroyed nearly 2,000 years ago, contained knowledge more valuable than any quantity of empty real estate among the stars. The loss of that knowledge impoverished humanity far more than our failure to colonize Jupiter's moons. What we create and preserve matters more than how far we spread. Perhaps the proper response to cosmic vastness is not ambition, but appreciation. Consider what we already possess, a planet of staggering beauty and complexity. Earth has been shaped by 4.5 billion years of geological and biological evolution into a world of extraordinary diversity. Mountains rise from tectonic collisions spanning hundreds of millions of years. Oceans circulate heat and nutrients through systems we barely understand. Atmospheres filter radiation through processes we are only beginning to appreciate. No other world we have discovered matches Earth's suitability for life as we know it. Mars is a frozen desert, with air too thin to breathe. Venus is a hellscape of crushing pressure and sulfuric acid. The moons of Jupiter and Saturn harbour buried oceans, but nothing like the surface environments where human civilization evolved. We already inhabit the finest world we know of. The urge to leave it often rests on assumptions about cosmic real estate that observations increasingly challenge. A biosphere containing millions of species, each representing billions of years of evolutionary refinement. Every organism on Earth descends from common ancestors who survived catastrophe after catastrophe. Asteroid impacts, volcanic winters, ice ages, mass extinctions. The genetic heritage we share with every living thing encodes successful solutions to every environmental challenge Earth has posed across deep time. This biosphere is not a stepping stone to somewhere better. It is the destination, the product of evolutionary processes so lengthy and so contingent that recreating anything similar elsewhere might require billions of years and cosmic luck. A species capable of art, science, philosophy, and love. Humans alone among Earth's creatures can contemplate their cosmic context, can create beauty that outlasts individual lives, can accumulate knowledge across generations through writing and teaching. These capabilities emerged exactly once in 4 billion years of terrestrial evolution. Their rarity suggests they might be equally rare throughout the cosmos. Cultures spanning thousands of years, accumulating wisdom across hundreds of generations. The philosophical traditions of ancient Greece still inform modern thinking. The mathematical discoveries of ancient Mesopotamia still underlie contemporary engineering. The artistic achievements of every civilization contribute to a human heritage that transcends individual lifetimes. Technology is permitting us to understand stars we can never visit, to see galaxies whose light departed billions of years before our planet formed. Modern astronomy allows humanity to comprehend cosmic scales utterly beyond any possibility of physical exploration. We can know the cosmos without possessing it. We can understand without conquering. This capacity to comprehend what we cannot reach might be the distinctive achievement of intelligence in our universe. Not expansion, but understanding. Not dominion, but appreciation. We stand at a privileged moment in cosmic history, early enough that the universe still teems with accessible energy, late enough that planets and stars have formed in abundance. We exist during the brief window when intelligence might contemplate its cosmic context before the universe's long decline into cold darkness. The recognition that we cannot expand indefinitely does not diminish this moment. It clarifies what this moment is. We are not destined to become a galactic civilization, but we are something remarkable nonetheless. We are a species capable of comprehending the cosmos it inhabits, even if it cannot possess it. We can see farther than we can travel. We can understand more than we can control. We can appreciate vastness that we can never fill. What then should we do? If cosmic expansion is impossible, if our reach is fundamentally limited, what does that mean for how we should live? The answer is not nihilism. The answer is not despair. The answer is focus. If our presence in the cosmos is limited, then what happens within that limited presence matters more, not less. The quality of civilization we build matters more, not less. The wisdom we accumulate matters more, not less. We cannot spread infinitely, but we can infinitely deepen our understanding, deepen our wisdom, deepen our appreciation of the cosmos we briefly inhabit. We cannot last forever, but we can make the time we have. Matter can create works of beauty and knowledge that justify our existence regardless of its duration. We cannot escape mortality, either individual or civilizational, but we can face mortality with grace, can accept our limits without surrendering to despair, can strive toward greatness without pretending that greatness requires infinitude. The dream of galactic expansion was always partly a dream of escaping death. If our species spread across billions of stars, surely something of us would survive any conceivable catastrophe. If our civilization lasted billions of years, surely individual death would lose its sting, each person a temporary manifestation of an effectively immortal whole. But this dream was based on an error. Cosmic expansion would not preserve what matters about humanity. It would merely spread copies that would immediately begin diverging from each other and from us. The humanity that survived would not be our humanity, would not preserve our languages, our cultures, our values, our memories. It would be our descendants in only the most technical genetic sense. True preservation of what matters requires not expansion but transmission. The passing of knowledge, wisdom, and values from generation to generation within communities small enough to maintain coherent identity. This transmission is difficult. We have discussed at length how it fails across the timescales required for interstellar travel, but it succeeds across shorter timescales. Human civilizations have transmitted knowledge across millennia. Human cultures have preserved values across centuries. Human families have maintained memories across generations. This limited success is not nothing. It is in fact everything we have, and it is enough. Human expansion will likely halt within a few hundred light-years of Earth. Beyond that boundary, distances impose timescales that exceed our capacity for coordinated action regardless of technology. We will establish daughter civilizations on nearby worlds, if we sustain the coordination necessary to launch such missions in the first place. Those colonies will diverge from us and from each other. They will develop their own languages, cultures, technologies, values. They will become, in time, something other than what we are. And this is not failure. This is the shape of what intelligence can achieve in a universe governed by physical laws that do not accommodate our aspirations for immortality and infinite expansion. We want it to last forever. We will not. Every human, every civilization, every species eventually ends. We want it to spread everywhere. We cannot. Distances impose timescales that exceed the persistence of coordination. But we will have existed. We will have wandered. We will have reached as far as our nature permitted. That is enough. The cosmos does not owe us infinite duration or unlimited territory. It owes us nothing. The universe operates according to physical laws that do not prioritize our preferences or accommodate our dreams. What we have this moment, this world, this opportunity to understand and appreciate, is gift enough. The question, how far could humans ever actually go, receives its answer not in light years but in human nature. We could go far enough to matter. We could go far enough to establish presence on worlds beyond our birth planet. We could go far enough to prove that intelligence can propagate between stars, even if it cannot remain unified across them. We could go far enough to establish something worthy of the cosmos we briefly inhabit, but we cannot go forever, and that boundary, though it falls far short of galactic dreams, is nothing to mourn. It is simply what we are. Beings who reach, beings who wonder, beings who strive towards something greater than ourselves, knowing that the striving matters more than the destination. Human expansion ends where human coordination fails, and human coordination fails far short of galactic scales. No matter how advanced our propulsion becomes, no matter how sophisticated our artificial intelligence grows, no matter how clever our engineering, we cannot escape what we are. The constraint is not written in the laws of physics, it is written in the nature of human society itself, in our inability to transmit unchanged purpose across generations, in our failure to maintain institutions beyond their natural lifespans, in the inevitable fragmentation that afflicts every human endeavour stretched beyond the limits of living memory. And accepting this does not require abandoning aspiration, it requires redirecting it toward the achievable rather than the impossible, toward civilizations that can actually persist rather than empires that must fragment, toward wisdom that accumulates rather than expansion that dissipates, toward presence that, however limited in cosmic terms, represents everything we are capable of being. The stars will remain beyond our reach, most of them, almost all of them, but the stars were never the point. The point was always here, in the wondering, in the reaching, in the brief, brilliant, improbable fact of our existence. We are matter that became conscious. We are cosmos, contemplating cosmos. We are the universe's way of knowing that it exists. That is enough. That is more than enough. That is everything.